Hello and good afternoon, Geek Speak attendees and listeners. My name is Mary Noble, one of Samtec's technical marketing coordinators, and I'm happy to be joining with you today. Today's Geek Speak is going to be a little bit different than normal. It's called Ask Me Anything, or an AMA with our SI experts of Scott McMorrow, Richard Melitz, and Isfan Novak from Samtec. So just a couple of things before we get started. If you do have a question, it comes up. You can either submit it through the Q&A link, not the chat dialogue, or you can just raise your hand in the chat, or you can just blurt out if you have a question as well. This is just going to be more of a talk and a discussion. We did have a couple of questions come in ready to our geekspeak@samtec.com email address, so we'll just begin with that. So without further ado, I'll introduce Scott and our presenters. Scott, how are you today?
I am good, Mary. Yeah, we're doing good. Beautiful day up here in Maine. Warm weather, blue skies. We love it. Still have color on our trees a little bit. We're about halfway through the fall. Today we're going to do an AMA, and our talkers will be Rich Melitz, and I think most everybody knows Rich. He's been heavily involved in the IEEE standards work that is being done, and was is essentially the curator and the programmer for most of the COM software. Then Isfan Novak also comes with doesn't need an introduction. He is a luminary in the industry, and we're glad to have him here. All right, so we have a couple of starter questions that we came up with, and then we're going to go into some of the questions that are the participants, you participants, have submitted to us in advance. And there's a lot of really good questions. We won't answer them all in this time, but we're going to start with Rich Melitz. How much margin is needed, Rich?
Well, it's DOE, design of experiments, or sometimes more importantly, depends on experience. So it really turns out that a lot of what we do in analysis is just that analysis, and it doesn't really relate to what our product margin, what our product quality is really going to be. So the challenge is to understand how the parameters that we measure relates to what we ship, and our kind of yields right there, and that's really a business decision. So some folks can just know because it's their experience, and some folks get that experience by making lots of measurements and either intuitively doing a design of experiments, or actually scientifically doing a design of experiments to determine the interrelationship between any parameter that you measure and the outcome that would be desirable for your company, which would be selling products or not having defects, or how many defects are okay. So it's very much a business decision. Thank you.
All right, fantastic. And that'll feed into my question, which is, and I think I'm going to go with Isfan first. So where do you see the break-even point between horizontal and vertical power delivery, Isfan? Isfan? You're muted.
Yes, thank you. Thanks for the reminder. So I think very soon we may see a gradual transition to vertical power delivery, even though these break-even points are never a clear cut and never, very sharp in the technology history. These tend to be more gradual transitions, because even though vertical power delivery even today would benefit a lot of the high current designs, but if the additional infrastructure in the components, the placement of the pieces in the chassis, and so on, if All of those are not available yet. Then the transition, even though just from the power distribution point of view, it would make sense, it is not that easy. But again, just my personal guess, the minute we have widespread current demands in the kiloampere ranges, then the vertical power delivery will become much more widely used. Right now, it is more an experimental phase.
Okay, that's a good answer to that question. Yeah, as we start running 50, 100, 300 amp processors and switches, then this becomes kind of an interesting problem in how do you deliver the power, and how do you deal with the effects on signal integrity and power delivery. Horizontal becomes kind of a pain when we have high performance differential pairs and they perforate. You have large antipads which perforate the planes, increase the spreading inductance and the spreading resistance, and so we'll get there. It's the other thing I think here is that we don't have a good standard footprint for putting things on the back and back of boards vertically, either on the or even on the top if you wanted to vertically power it from the top. So without those kind of standards, the transition's gonna be a while. Let's talk about, as a group, let's talk about additive manufacturing in signal integrity, short term and long term. And I'll just start. Well, actually, Istvan, you go ahead and start because you've been involved in additive manufacturing.
Yeah, so as much as I understand the current state of additive manufacturing, for the signal integrity segment, one option is to create interconnects like planar PC boards or packages, or replacing connectors by 3D manufactured pieces. The current drawbacks and shortcomings, in my view, as I understand, is that the material properties are not really well suited for low loss, high speed interconnects. When the physical piece is short, small, then it may not matter that much. But certainly the dimensional accuracy, repeatability, surface roughness, which appears in a different way, but it is still there with 3D manufactured pieces, all that would need to be hashed out. So right now, in short term, I believe it is the small pieces and the small volume, quick turn, samples and so on, just proving out concepts before expensive tooling goes in. Long term, as soon as the material properties will get way better, and I purposely didn't even ask PI, because right now most of the 3D printed pieces that we tried in terms of conductivity are bad enough that for high current applications I wouldn't think about using them. But long term, of course, it can change. So it depends on how the technology evolves, what kind of materials can be 3D printed. It has a lot of potential. That's my very quick summary.
Yeah, and I would add to that, there's the conductivity of copper is or of the metals is horrible in 3D printing. It's about a tenth of or worse than that of 100% copper. So that impacts the signaling path. It is possible to use 3D printing for shielding, right? Because we don't need to have perfect conductors. We can accept, as long as we have enough thickness in the conductor, we can still use that for shielding. For high speed return paths, maybe if the structure is large enough. The other thing that concerns me about 3D printing, and I keep asking this question, is in manufacturing, what's the beat rate? How many of these machines do you need? How long does it take to do the printing? And then how many of these machines do you need to effectively do the same thing that we do with insert molding, standard molds, and stampings and things like that, where we can, create thousands of things in an hour. It's much harder to do with 3D printing unless you have an entire assembly line with them. So I think it's a great technology. I just haven't found a good place to use it in what I do. And Istvan's tried it in terms of quick testing of concepts, and it works quite well there as long as you don't have to deal, as long as you can accept the reduction in performance. So I'll go to my question, which is, so Rich said, well, how much margin is needed? You do a DOE. So I asked the question, a DOE on what? Measurements? Lots of stuff written on the accuracy of measurements. When we get into something for a large system, you can't measure your way out of manufacturing issues and margin issues, right? Because you can't measure enough things. And you can't measure them all simultaneously, which is what the system's doing. So we resort to simulation. So the question you've got to ask is your simulator accurate? Can you do enough simulations fast enough to create the models necessary to perform a design of experiments of an entire system? And so in my experience, the first thing, and this is, I'm a little unique in that, I would suggest that everybody do this, is that before you use a three-dimensional solver or any kind of electromagnetic solver, any kind of numerical method, you must characterize it, because otherwise you can get computer-based hallucinations. They're no better than asking ChatGPT about an SI problem. You ask ChatGPT about an SI problem and you'll get all kinds of interesting, weird, and wrong answers. You'll also get right answers put in there. You'll get the same thing with the solver.
If I just may inject something here, because here your question is about simulator software, but I sometimes see the same kind of one-sided view or one-sided expectation regarding measurements. When people assume that measurements show quote-unquote the real thing, well, yes, it will include everything that we might have forgotten to model in a simulation, but the measurement will have its own artifacts and errors and potential mistakes done by the user. So I would very strongly encourage everyone not to blindly trust measurements either, without what you just said, Scott, carefully characterizing the tool that we use to benchmark the piece we are looking at. Whether it's measurement or simulation, it's equally important.
It's equally important. I like to sort of cut in here. It's equally important for simulation and measurement, but and to mention DOE again or statistical methods. The deviation from the normal statistics of the error function of what you think you're getting to what you predict is indicative of whether you missed physics or missed assumptions or not. So being really skilled with understanding the nature of predicting through large sets of data can give you insight into whether the actual experiment that you've made is correct or not, or just missing parameters or missing the cofactors that are ever so important.
Right, exactly. And that's so in any kind of simulation, any kind of measurement, we have to characterize, and we have to characterize it against physical entities, benchmarks. There's one person on here, Al Neves, who has a business building test boards for characterization of solvers and of measurements, and you use both. And it's important. And when I talk about characterizing just as a solver, I can guarantee you, box stock out of the box, every solver's wrong. Or what I'd rather say, a better way to say that is its error bounds is huge. So, and I see so many people that use their tools as a magic black box to press, make a model, press a button, and boom. So you start out with those things that you know that you can have analytical solutions for or good measurements of, and then use that to characterize the solver in terms of how closely it gets to the answer. But at the same time, the solvers also have their own statistical error bounds. And we've talked about that in the past. And so it's incredibly important to do that in terms of speed and accuracy. There's always that trade-off, but there's also settings and things that you can do that will give you more performance in the solver with the same accuracy or equivalent accuracy. So it's really important. And we spend thousands of hours in characterization, thousands at Samtec and in previous lives. So I just can't stress that enough, because at 112, it's hard, 224, it's damn near impossible. And at 448, it's going to be magic to get signals to propagate anywhere. All right, let's flip to the next slide.
I'd like to add one more thing for additive technology. You're all talking about 3D printing, but just to remind you that packages are additive technology.
Well, yeah, but they're additive
printed,
sheets. Yeah.
No, they're printing.
No. The most widely used material in the packaging industry is the Jinimoto buildup films, ABF films, and those are literally films.
Yeah, but the etching is additive.
Well, yeah, it's electric.
It's not subtractive.
Well, but so is a printed circuit board, right?
No,
plating is an additive process.
The etching is not. Etching is subtractive.
Is subtractive. No. Yeah. No, exactly. Right.
But the so the base material is subtracted with acid, and it's just the opposite for packages. So it's actually considered additive technology.
The base metals, yes, not the base dielectrics, though.
Right.
Okay. We agree. We just see things from two different perspectives. Yeah. All right, let's go a flip to the next slide.
Yeah, before we go to the next slide, there was a question in the chat. It says, for the engineer on a tight budget, what tools are most helpful to the SIPI engineer?
Your brain.
Hire Scott.
Yeah, so that's a good question. It depends on what you're doing. If you're at, I'll call them lower performance PCI Express Gen 4 and below, for example, you can get a lot of legs out of 2D solvers, planar board solvers, and 2.5D kind of solvers, like a Symbior, for example. It's a very good tool at a good entry level that gives you all of the things you need to do basic, simple, trace design, minor launch designs, and some board simulations at a good price point. And there's others. Unfortunately, all of these tools are incredibly expensive. So If I were going to recommend one, and if this is not an endorsement, but it would be something like Symbior or Hyperlinks. But Hyperlinks gets pretty spendy when you add on all the extra stuff beyond the 2D solvers. So otherwise, you're starting, any kind of three-dimensional solver is going to cost 60,000 to $100,000, and you're going to need some serious compute hardware behind it. So I hope that answers the question. Okay.
My opinion, tools are teaching teaching vehicles, and it depends on what you need to learn. Is depend upon what tool you need to use. So if you're a very experienced engineer, you might be able to just use pen and paper.
Very true. Very true. So I like this. This is, I think this is from Dan. Yeah, Dan Chirpich. And I love the first question. And I'm going to ask Istvan to start there. What are your thoughts on creating formal specifications or processes for power integrity? Why isn't there one? It seems that PI is mature enough to at least outline the process for the industry to follow.
Well, yes, that's an excellent question, and it has come up in recent years multiple times. And unfortunately, my answer is that I'm not too optimistic in terms of finding a formal specification or formal standard. Well, it certainly depends on what we mean by it. Like, could we standardize requirement items? What the chip makers and the chip users would need to use? That is probably the lowest hanging fruit, so that everyone would supply the information in the same, I would say, format or same kind of parameters. But if we think about like specifying a form factor or specifying a quote unquote signaling, like the physical layer specification in any high SerDes specification, that is much less likely to happen simply because in signal integrity, especially luckily as we move to higher speeds, luckily in that sense that we have to localize the interconnects, otherwise we won't be successful. In power distribution, on the other hand, that wouldn't make sense, and it is, even if we wanted to, even if we give up all common sense considerations, it may not be practically possible. So if we cannot separate the rest of the system from what we try to analyze and look at or specify, then it becomes an impossible task. So in my view, that is the main reason why we still don't have anything. And in my view, that is the reason why very likely we will not have one.
Yeah, I would follow on to that and say the big problem with power integrity is the silicon and the package. And if you do not have control of that design, you're operating blind. And in general, semiconductor companies do not like to reveal that information in any kind of modeling way, because it reveals way too much about the quality and the capabilities of their designs. It reveals an exceptional amount of information, and so we end up with these impedance targets at the printed circuit board, which in these days is actually far removed from the power behavior of the package and the and the silicon. And so it only solves a part of the problem. It doesn't solve everything. But I'm with Istvan. We're not getting more than that from them, and most manufacturers won't even give you their target impedance specifications. So it's an unfortunate thing. But until there's massive system failures because of power, that the silicon manufacturer could have solved by providing specifications and models, we'll never get to a formal specification or process. That's my opinion.
Wonder if I could add in here.
Yeah.
I think to have a specification, first of all, you're going to need some kind of a compliance. Do you pass or fail? Well, that's okay. Where? That's called a test point. Okay, so I challenge the industry to come up with a test point that's kind of a network. How do you put a test point in Jello? I don't know. So unless we can define where the Jello is and how it flows, we don't have a test point, which gives about the only thing that I think you might be able to do is something like what they did in the IBM, in the Intel, not Intel, the IEEE 370 standard, which is really not a compliance standard. Says these are recommended methods that should give you some kind of quality. That's about the best I think you can hope for any kind of standardization, which is even much more difficult, I think, for power than it is for something that you can put a note on and measure it.
Right, and that's essentially the problem. Is Istvan talked about the concept of localization. Localization is the concept of basically having enough ground return path around a signaling structure to contain electromagnetic energy so that it's is contained within a local region. Unfortunately, you can't do that with power. Power sweeps in the entire extent of the entire system, the entire package, and the entire piece of silicon. So it's a localization. It's a non-localized system where if you want to get good answers, you have to simulate everything. And getting all of that information is often extraordinarily difficult. If you happen to have designed the chip, designed the package, and designed the system, you can do it, right? But even then, getting silicon groups and package groups and board groups to all work together on that has always been difficult in the industry, and it did a lot of
very
products.
Good point, Scott. It's an excellent point, and just one thought on that is someone may ask, okay, so but still, why can't we do something similar what we do on signal integrity, like localize it? I just mentioned earlier that I don't think that it makes sense or would be feasible, but why? Because when we think about high-speed signaling, just think about a massive data flow over multiple parallel interconnects, whether it's PCB traces or connector pins or cables. We break up the huge amount of data flow into smaller streams. That's either a single-ended or differential interconnect, and that is being designed to a given specification. For power, even though hypothetically we could do that, like feeding every single signaling cell with its own power, which could be, by the way, then at that point standardized, but that absolutely wouldn't make sense because it would require so many individual power domains that it's just practically impossible. So we combine for an unknown number of signalings, unknown in the sense that every chip, every user may decide a different number of signalings combined for feeding them. That is why the target impedance, or however we call it, or impedance requirement, or transient time domain requirement, will be different for each major chip design. And that's something that I don't think will change in the future.
All right, that's a great answer. Let's move forward to the next slide, and if it's not the next slide, there's another slide. No, let's go to the next one. This is because this connects. So this is a question from Saeed Bokhari, and we want to simulate a 3D simulator, a BGA differential pair comprising a positive and negative ball, and its neighboring balls are ground. So it's ground, positive, negative, ground. That's easy. What happens when power gets interspersed in there? So here is the dirty secret. Everything in our simulations of differential interconnect or even single-ended interconnect work really well with the concept of basically breaking down the system into linear cascaded elements. And that works only if the entirety of the interconnect is localized and doesn't burst energy somewhere else. Now, nothing's fully localized, right? Crosstalk is non-localization, but we can limit its extent in a good differential pair signal integrity design or a signal integrity design. As soon as we introduce, and the reason it works well is our boards are referenced to this net that we call ground. And there's a huge amount of ground copper and ground vias, and it's therefore inherently ultra low impedance, which means which localization. Low impedances provide a sink to all that energy and keep it from going out to someplace else. As soon as we pull one ground ball and one set of ground vias and insert a power ball and power via in an asymmetric fashion between the positive and the negative side, in this case, power, positive, negative, ground. Well, what's going to happen? The positive signal is going to have its return. It's going to generate an instantaneous return in the ball and the via, and it now is connected to the entire power network from your plug in the wall all the way to your silicon, through your package, your planes, and everything. So you've suddenly connected it to a very, very uncontrolled network. And if you've ever done power simulations, we do these power simulations of boards where, as long as the impedance profile is below the target up to say 5 megahertz, 10 megahertz, 20 megahertz, we're good in most cases. As single-ended signaling, it's a bit different because there's more noise in the power system. But above that, when you do power system, we hardly ever do power system simulations above a few gigahertz. Why? It's a mess. There are resonances everywhere. Well, guess what? As soon as you open up the return path to ground and put a power ball there and a power via there, we're now coupling signals, energy, crosstalk into the power network. And we could characterize that, but it's really, 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 really hard. So the answer to your question is don't do that. Don't reference any signal to power. Now, if you have an array, a BGA, normally what you have is two signals, ground on the left, ground on the right, ground above, ground below each pair. It is sometimes permissible to have powers of the same type at the diagonals. They're further away, and they are coupling symmetrically. So whatever power system noise and the essentially the power spectral density of the power system is being applied to both points, and except at ultra high frequencies above about 100 gigahertz, they're correlated in both profile and time, and they basically cancel out unless you get outside of the common mode range of the receiver, which is an entirely different problem. So there are way too many designs out there. You can look at them, and I can immediately tell you, I can often tell you which pair is going to have a problem if somebody had to compromise and pull a ground and put a power in. You can basically look at it and go, okay, your signaling is going to be worse there. You're going to have higher noise. Your comm is going to be lower. And it's all because of a choice to put a power next to a signal. So never, ever, 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 ever do this. And if you have to, do it symmetrically and still make sure that there are grounds to carry most of the instantaneous return current.
Unless your receiver has power to burn. Because if you know the maximum spectral content of the power noise, with enough power in the SerDes, it can compensate for that.
Oh, but yeah, it can't, right.
But it's orders of magnitude more power than would be in like a data center switch.
Yes.
Per picojoule per bit. At a couple of hundred picojoules per bit, yeah, you probably could do it.
All right, let's flip back.
2 picojoules per bit, you're in trouble.
Oh, yes, absolutely. So let's flip back to the previous slide now. All right, so a lot of SIPI. Okay, so we have an SIPI designer, designs links at 10 gigs, consuming 10 to 20 amps of current. And so, we know these are not hard designs anymore. We used to think they were hard. They're not anymore. But if you're going faster, so in designing high-speed serial links, all the signal processing is being done by the chips, and it's massive and it's enormous because they're all using digital signal processors now in the latest, about half of the 112 and all the 224 design. So learning signal processing for you as an SI designer, it's a worthless, if you are intellectually interested in it, it's great. But it doesn't provide you any benefit because your chips are taking care of all that, and other people have spent their careers architecting this stuff. Your best bet as a new designer is to have a good simulation tool that you have correlated both measurements and against benchmark structures like simple transmission lines and coax and things like that, and resonators. And then work with vias. Everything in an SI design is about the vias. We pretty much don't care about the traces. Right now, today, you can go to a fabricator, say, I need a trace of X width, a trace of this impedance on these materials, and they'll give you a good trace design, right? And you might tweak it a little bit. But the thing that you really takes time to understand is how that vias interact and how do you get the localization that you need. And remember, just for localization, we have to, as we go to higher and higher bandwidths, the effective bandwidth and the effective lambda of the signals is shorter, which means that things have that it becomes harder and harder and harder to isolate. Which, that's why we have coaxial cables with grounds all the way around them, and coaxial connectors that are fully shielded with grounds. If you go from coax to coax and do that ad infinitum, everything works really great. As soon as you go into a board and dip through vias, everything breaks up. So spend your time as a young designer learning how vias work, how to space them, how to control impedance through them, how to keep energy from flopping around inside of the boards. That becomes really important on number C when you're designing with RF circuits. Your signals are in your power system are essentially crosstalking and radiating huge amounts of energy. And those RF circuits are dealing with microvolts. So in general, if you look in many systems with RF, they're put in shields. Why? Because there's energy inside of your chassis. So that becomes a much more difficult problem, but all of your work in localization will help you better understand the limits that you have there. Designing PDNs for high current, I'm going to defer to my esteemed colleague Istvan to tell us how crazy it is.
Yes,
You're on mute.
so whether it is hundreds of amps or thousands of amps that people are talking about in these days, somewhere we have to give up all of the preconceptions and we need to open up our minds. As it has been mentioned multiple times here, localization is not practically doable for these PDN circuits, which means instead of focusing just on the immediate little detail of the circuitry that we want to or have to design, even if the other pieces are not designed by us, we need to look at them and consider them as a minimum. So we have to open up our view in multiple ways, like we have to be aware of things more than the immediate localization of the little detail, like selecting a bypass capacitor, where it goes, where can I put it, how to connect it, all of those will immediately matter. We also have to open up our minds to things that might be, urban misses or just things that we might not think with. For instance, just naming two, for instance, many times for people who understand that for very high-speed signaling, the roughness of the conductor is a degrading factor. So if that is linked to increasingly higher frequencies, one might think that as we go to lower frequencies, it matters less and less. On the other hand, if we go through the details, we can easily convince ourselves that it is equally, if not even more, degrading the DC distribution. Similarly, when people just think about the high-speed considerations that, yes, if I was to have a sharp writing or corner with a high-speed trace, there is a lot of debate whether it is bad or just a concern. So let's just state generically that it is a concern. Whether it is unacceptable or not, that's a different question. But again, that might give the impression that as frequency goes down, all of the related potential concerns and issues just magically disappear. But as with the roughness, with DC and low frequency distribution as well, if we have sharp corners, that is not necessarily good. So all of those details would need to be synced with. We need to remember that when we have to push high currents, the thermal considerations, which is a different engineering principle, those will also need to be at least looked at, not necessarily by the same engineer, but if the engineer doesn't know what questions to ask, what help, additional disciplines may need to be provided, that is usually where we might run into problems, and that actually might link us to sub-question C on this slide. Close to RF circuits like 5G radios or anything sensitive low signal. If we have a mixed design where we have high current, high power system co-located with a sensitive RF or analog, maybe audio circuit, or maybe just a high-speed, high-resolution analog to digital converter or digital to analog converter, then we again need to remember that power most likely is not easy to localize in dedicated circuits like things where we can compartmentalize physically things. We may have a better chance at least to build in barriers, and that goes back to what Scott mentioned about 3D printing applications, that whether it's 3D printed or in any other way, just thinking also in terms of electromagnetic compatibility, not necessarily violating any compliance requirements, which are usually 3 to 10 meters from our offending system, but more like how, just back to this question, how our own noise sources may interfere with our own circuits within the same system. So that requires a little field consideration, wave propagation considerations. So when it comes to what kind of new knowledge may be needed, just being aware of those, again, not necessarily requiring expertise, the deep expertise, just awareness to know where to ask for additional help and where to bring in additional help if needed.
Exactly. One of the things that is good about the way chips are designed is that the high power core section is essentially isolated, right? All of the SerDes are in the outside periphery, so you have the core area, and that's where we're delivering power to the chip. The high power, hundreds and even thousands of amps up into a particular chip, but that's still causing energy to go out through the planes, right? There's waves propagating out there, and so we have to be very, concerned about how that affects our signaling. So let's go back to the previous set of slides from Dan. He had some more questions. These are all great questions, by the way. Thanks for those that sent them. Okay. Let's.
Yeah, I was going to say there's a couple questions in the chat here,
Oh.
Scott, Ms. Bon and Rich.
Okay.
So I'll start with Dan's question in the chat. Says regarding Said's question, could you speak to how to think about power ground noise coupling to the differential pair? And do you think about magnetic fields including noise on the differential pair?
Yes. So in the case of, there's obviously inside of planes. So one of the things that we do with high-speed signaling today is to use sandwiched strip line construction with ground plane above and ground plane below. What does that do? That effectively, with ground vias to around the board, that essentially localizes the planes and partially cuts off propagation of noise. Because remember that those huge amounts of power are still flowing, and they're radiating inductively in the planes and causing plane waves to come through and pass by signals. The good thing is that our differential pairs are spaced pretty close together. 10 mils center to center, 15 mils, 16 mils center to center. Wavelength wise, that's really small. And so where we get, as the wave passes through, it'll pass by one side of the pair, the positive, and then the negative. There'll be a time delay. That time delay causes noise, right? There's a differential signal that's caused by the power wave passing through. But it happens so fast, we're talking less than a picosecond, that effectively at the frequencies we're working at, it's canceled out differentially. It's not an issue. It looks as close to simultaneously as possible, and it's really hard to even measure that. But there are cases where you can place a signal trace close to the edge of a plane where you can get back reflections off of there, and then it gets a lot more complicated. So anything to add, Rich or Ishvan? Now, if we're doing signaling with ground on one side of the strip line and power on the other, which they do in DDR, they only do it for the well, they used to do it. I don't know if they do it anymore, for the address command buses, because that was lower frequency than the signals, and there was more time to recover, to basically clock the signal, clock the command in. And so there's some isolation. And what we did in the case of those designs, to make the packages cheaper, we use power and ground planes for the memory boards, the memory modules. We sandwich the address and command bus between the power and ground planes, and we try to create a continuous path all the way through. If you switch from power ground-based signaling to ground-based signaling, or vice versa, you get modal changes that happen there, right? Because you have to close the return, and that necessarily has to go up through bypass capacitors. And so the response time in that transition is horrible.
I think the thing is that you sort of indicated that there is a low frequency response. Okay, in most SerDes that tends to get rid of a lot of that. However, there is also another fact, is that the common mode in the CD and DC common mode return loss, I would be, I guess, CD return loss, is fairly high. It could be 4 or 5 dB. So you have to consider that if you don't have good common mode termination, you could incur effects of the power noise that are not are due to the delay difference between between the two pairs, where the noise is on one, where you think it's on the other. There is a time difference between there, but the voltage on that time difference is fairly small because the frequency of the power is fairly low. So. But these common mode can be very troublesome if you have very poor common mode conversion.
Right, and there's one place where you do have to be careful, and that's low frequency magnetics penetrate things really well. So switching regulators are full of low frequency energy. And it is, I've seen cases, and this goes back 20 years, right? 25 years, where somebody decided they would route a differential pair right underneath the regulator on the plane below. And there was only half-ounce copper there. And what happens is the magnetic field penetrates the copper and injects itself and basically couples into the signal, and you end up with a low frequency below one, say below 5 megahertz coupling into there, and that will drive some SerDes wild.
Yeah, it's fun. And did some experiments for me on some of that. The bottom line is stay away from really noisy switches. Don't get too darn close to it.
Don't get
these things are orders and orders of magnitude more signal than what we're talking about.
Exactly.
Yeah, and Rich, the thing that you mentioned, there was a Samtec Geek Speak on that topic. How much common mode is too much?
Oh yeah. That's true.
Yeah, so that's go back and look at that. Yeah, I'd forgotten we'd done that.
But that was a lot. That was, I mean, it was something that you would. I mean, when I looked at the amount, it was like, holy smokes, that's huge.
Oh
just
yeah,
don't do it.
Huge.
Just don't do that.
Right, because most inductors have a basically an open slot in them, right? And so in switching regulators, and sometimes they're positioned at the bottom of the regulator, right at the board level. And so all that energy just goes right down into the board. Others have it on the top and others do it in other ways. Istvan did quite a nice study on that. But I think we're up at the end of our time here.
We are.
Yeah, I was going to say we have a couple more minutes. I have 2 questions, I guess, left in the chat.
Sure.
Okay, so the first one is, how does SI design and development integrate with mass data for data analysis?
Repeat that again.
Yep. How does SI design and development integrates with mass data for data analysis?
Oh, that's an interesting question because, if you take a look at, let's take a package, for example. If you really want to understand the electrical performance of a package, you have to look at a very, very large section. You have to look at the power simultaneously with the signals. And let's just take one quadrant of a package. Well, there are a lot of power balls. There are a lot of signal balls. There's a lot of energy floating around. And so what you end up with is simulation and modeling, which can have, I've had S parameters as large as 1024p files. 5, 6, 7 gigabytes of S parameters going up to 50 or 60 gigahertz. And that becomes a huge big data problem in terms of processing it, because there aren't any tools that can process that, commercial tools that process files that are that large. But then trying to generalize that, what if you wanted to do a design of experiments on changing, material changes, etch changes, via changes, all of that, it becomes daunting. Which is why we love localization. When we can localize, we will with differential pairs. But go ahead, anybody else?
That's sort of an open-ended question too. I mean,
it is.
When I look at that, the other way to take that is like, oh, let me take a heat map worldwide of data problems where they have high error ratios. So therefore, it's sort of like it's like, yeah, the data is there, but you use the signal integrity to debug why you have these data anomalies, which is very important to actually the end customer for a data center, which is kind of like the IT manager. He's got some problem. He doesn't know why. He doesn't care why. He just sees a heat map, and then, hey, company X, go fix your problem, and then that's where you bring in the signal integrity.
Yeah, exactly. And there's actually a guy in the industry, Chris Chang, which a number of you know. He's been a pioneer in using AI in system engineering. And his first place for using it was a simple data problem, which was they were building storage systems, massive storage systems, and you just can't have data errors in them. So they developed, they have massive statistics that have been captured on their storage servers, and all of the drives in the system. And they basically captured all that information in terms of the data error rates and retry rates and all of that to come up with predictive analysis of when should they go out and just, can they do early prediction to replace drives rather than waiting for them to fail. And it turned out it was very successful and that's one of those targeted problems. When it comes to general signal integrity and power integrity, you just can't get enough data to do a good system-wide analysis of that. So you have to break it down into small first principle segments. As large, you do the largest segment that you can, but it is difficult.
Okay, then there's a final question here, and then I'll go to the last slide. So the final question is, what are the negative implications of DDR signals routed near the edge of the PCB?
So the signal itself and the trace itself, not so much a problem because, again, we're talking a strip line well, in case of DDR, it's a single-ended signal, so it is getting some noise. And the worst place to route, if you don't know this, the worst place on a board to route any signal or place any via, especially placing vias, is near the corner, because you get a double reflection. And it's like being at a pool, at a community pool, when adult swim time is ended and the children jump in, and where are the biggest waves? At the corner. And that's what happens in a power system. So the big deal is to keep your vias away from the edges and corners, because you get that back reflection off of the noise. And if you have other vias in that vicinity, they will pick up and cause crosstalk. And you can see this if you, in packages, that's exactly what you do. If you look at a BGA bus coming out to the balls, oftentimes they fan out to almost to the corner of the device. And so what happens, the amount of grounds becomes sparse in that region. So if the differential pair was 3 rows back, and I don't know, you had a 3-to-1 signal to ground ratio to meet your noise requirements, well, that will in the middle of the package, but as you get to the edge, you're losing the return path grounds. When you lose the return path grounds, that means that multiple signals have got to share the path in the sparser number of grounds you have. And the worst place for it is near the corner of the package, because that's where we have compromised the amount of return path vias. And so I can look at a package and I can tell you exactly where the high crosstalk areas will be at, and it'll be any vias that are close to the edges in a DDR system, because when the DDR system is single-ended, that energy is just going everywhere. Any other comments?
No, I don't see anything else.
Well, this is fantastic. We're running a little bit late and people are still here, so it must have been interesting.
Yeah, so I was gonna, I guess, conclude here and say thank you so much to Isfan and Rich and Scott, and to all of our listeners and attendees today for their questions. If you have any specific questions or design troubleshooting questions, please email our SIG group at sig@samtec.com. In the next couple of days, or 24 to 48 hours, this presentation and recording will be on our GeekSpeak landing page. And we hope you will join on the next GeekSpeak in November. And thank you again so much for joining us today.